Hello all, welcome to the fourth lecture on the topic of optics and lasers. So in the previous three lectures we had talked about the concepts of interference and diffraction and the different experiments and different types of diffraction which are involved. We also discussed about using a diffraction grating and its resolving power. Now today we are going to start with lasers. So laser actually represents light amplification by stimulated emission of radiation. So L for light, A for amplification, S for stimulated, E for emission and R for radiation forms laser. Now in these terms, light you are already aware of, emission you are aware of, radiation you are aware of, amplification yes, in a sense you can understand, but you have not heard the word stimulated. So we need to understand how a laser works. But before that, we need to know what are the physical principles behind the working of a laser. So the theoretical concept of stimulated emission was actually given by Einstein in the year 1960. And C.H. Townes and his team applied it first to a microwave amplifier based on a stimulated emission of radiation during 1954. So it was then named as Maser, M-A-S-E-R. Now later, C.H. Townes along with a Sharlaw extended it to the case of light or optical light. And the first laser was built by T.H. Mayman in the year 1960. So a laser is actually a monochromatic coherent light source, and usually whenever we say that light is being absorbed by an atom, actually what the atom is doing is it is taking the energy from the light. So there is a transfer of energy from the light to the atoms. Now when the energy is being transferred from atom to light or photon, you call as light amplification, and this entire phenomena occurring in laser make use of the principle of quantum theory or quantum mechanics. Now we define a term called as population density, which is actually the number of atoms per unit volume at a particular energy level. So how many atoms are there at a particular energy level per unit volume of the material? So that is population density. So for an energy level E1, I will say the population as N1, and for an energy level E2, then the population is N2. And the incident light is going to have an energy which is equal to the difference between energy level E1 and E2. So the energy of the incident photon hν should be equal to the energy difference between the levels 1 and 2. Now basically photons traveling through a medium can result in three types of processes. First is absorption, then spontaneous emission, and then stimulated emission. Let's look into these one by one. So we start with absorption of radiation or light. So I am considering here a lower energy state or low energy level, then a high energy level. A photon is incident at this lower energy level. So the electrons in the atom absorb energy from the photon and they get excited and reach the higher energy state. So after absorption, you can see that the electron or the atom has reached the higher energy state. So I can give a simpler equation for transition. So if I have the atom A, then it absorbs an energy hν from the photon. Then once it is excited to the high energy state, I can write it as A star. Now the probability for this transition to occur from low energy state to high energy state is going to be proportional to the photon density, because the photon plays a major role here. The photon is being absorbed by the atom, then only it is able to go to the higher energy state. So I mentioned the probability for transition from energy level 1 to energy level 2 as P12 and it is proportional to the photon density rho of nu. So the proportionality constant is given by B12. 1, 2 represent from that, it's from energy level 1 to 2. And this constant B12 is known as the Einstein coefficient for induced absorption. Now the total number of atoms which undergo such absorption in a particular time delta t, I can get if I know this probability here P12 and how many atoms are there at this energy level 1. So if I have n1 number of atoms at the energy level and probability is P12, then the total number of atoms undergoing the absorption at a particular time delta t is n absorbed is n1 into P12 or n1 into B12 rho nu delta t. Now next let's talk about spontaneous emission. So once an electron or atom has reached the high energy state or an excited energy state, it cannot stay there for a longer period because the lifetime of electrons at an excited state is very small, that is of the order of 10 power minus 8 seconds or of the order of nanosecond. It's very small. So it tends to come back to the lower energy state. So when it comes back, what it does is it has to lose the energy which it had, and so there is an energy difference it sees from the high energy state to low energy state, and that energy is being released in the form of photons. So here the photons are being produced. So I can give the equation of transition as, say, A star was when it was in excited state, it becomes A once it reaches a ground state. Along with that a photon is emitted, so it is plus H nu. Now here the probability of emission is going to depend only on the energy level. There is no photon acting on the process, photon is only being released. So the probability P21, because it is from level 2 to level 1. So P21 for spontaneous emission can be written as capital A and 21. And A21 is called as the Einstein coefficient for spontaneous emission. Now suppose if the number of atoms at the excited state is N2, then the total number of atoms undergoing transitions within a time delta t I can get by multiplying the number of atoms and the probability. So it becomes within time delta t these many number of atoms, that is N2 A21 delta t number of atoms undergo the spontaneous emission or undergo transition. So now one more point very important to be noticed is that here the light is being produced on its own. So there is not going to be any correlation between the different photons coming out here. So that means there is no correlation, means each of them will be in different phase, and you can say that it's an incoherent emission. They are not in phase. And also they may not be monochromatic. They all will not have, because the energy difference can be different. So all the photons coming down may not be of the same wavelength or same frequency. So they may not be monochromatic. Now let's come to the next, that is stimulated emission, which is very important to be understood if you want to know how a laser works. So for that, what we are going to do is we are going to consider an electron which is existing in the excited state. So here spontaneous emission is not going to happen, but what is going to happen is there is an external radiation being given. There is an external source of photon being given. So a forced reaction is going to happen. So an external photon interacts with this electron in the higher energy state, and then the electron comes to the low energy state, as you can see here. So you already have an external photon acting here, so that fellow also comes out, and when the electron is transiting from high energy state to low energy state, it also releases an energy in the form of photon. So this is known as a stimulated emission. It is being triggered to happen. The emission is being triggered to happen. So you will get a stimulated photon and a spontaneous photon in this case. So the equation of transition you can mention as, say, the excited level, it is A star, along with that a photon is acting plus h nu, result into a ground level A, along with two photons which have come out, one spontaneous and one stimulated, that is 2h nu. So A star plus h nu is equal to A plus 2h nu. Now the probability of transition, once again it is from level 2 to level 1, so it is P21, but it's a stimulated emission, so the suffix is ST. Now this one is going to depend on the density of the photon which triggered the process. So the probability of transition is given as B21 into rho nu, and B21 is the Einstein coefficient for stimulated emission. And once again I can get the total number of atoms which undergo such stimulated emission for a particular time interval by multiplying the total number of atoms at the excited state along with the probability for transition. So that becomes N stimulated is N2 into B21 rho of nu into delta T. Now let's see what happens if a stimulated photon is being produced or when stimulated emission takes place. So you had one incident photon, a triggering photon interacting with an electron or one atom here, and it produces one spontaneous photon and a stimulated photon. What these are going to do is they are going to again interact with another atom and result in further production of photons, like one spontaneous and stimulated. So this keeps on going on like an avalanche process. So initially you can see that it was only one photon acting. Next you get two photons. Each of them acts on one atom each, results into 2 each, so it total becomes 4. Like this it goes on in the power of 2. So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, like that it goes on, and you get 2 to the power of n photons at the end. So many number of photons are produced at the end of the stimulated emission. So multiple stimulated emissions can happen. Or basically, if I consider the incident photon had an intensity, say capital I, then say n number of 2 to the power of n number of photons have been produced. So the resultant intensity is n square I, where n is actually the number of atoms. So resultant is, if you have many number of atoms, you can get a very high intensity light. So I had only one atom here, then 2, then 4, 8, like that it went on till 2 to the power of n. Like similarly I get a 2 to the power of n photons. Resultant intensity is n square I. So total intensity of the light, resultant light, increases if you have many number of atoms, or we can say that the incident light here, the first stage, has been amplified. Now let's go in depth about how the light amplification occurs and when stimulated emission can dominate, since it is very much required. So in a typical case, that is when the system is at thermodynamic equilibrium, we will say that the number of atoms at low energy level are more than the number of atoms at a high energy level. So N1 is much more than N2. So if number of atoms in low energy level are more, then there is more chance for absorption than the stimulated emission. So that means we need 3 important conditions for the stimulated emission to dominate. First one is that the number of atoms or the population at excited level has to be more than that what is at the lower level, or N2 has to become much greater than N1. Next, the probability ratio of the coefficients, that is B21 divided by A12, should be large. And next, you need a very high radiation density within the medium. So in order to achieve these conditions, There are three solutions. First one is known as population inversion. The next is the presence of a metastable energy level. And then you need the emitted radiation to be existing within an optical resonant cavity. So let's understand these one by one. First, let's consider the population inversion. So at thermal equilibrium, we already said that number of atoms at low energy level N1 is much greater than N2. So at thermal equilibrium, the ratio of atoms at high energy level to low energy level, say, is given by this distribution, statistical distribution, which is called as Boltzmann distribution law. That is N2 by N1 is exponential minus of E2 minus E1 by KT. N2 number of atoms in level 2, N1 number of atoms in level 1. E2 is the energy level 2, E1 is the energy level 1. So in a normal condition, you have N1 dominating over N2. And what we need is N2 greater than N1. So if N2 has to be greater than N1 in this particular expression, then the temperature T has to become negative. And practically we cannot go for a negative temperature. We do only at temperature above 0 Kelvin. So the only possibility is that you give an external source of energy and force the system to achieve population inversion. Force it to become N2 greater than N1. You have to give an external source of energy. So once you get population inversion, what can happen is a few random photons can trigger the stimulated emission, which we discussed earlier. And these stimulated emission photons, these photons which are produced now, can trigger more stimulated emissions. Trigger or induce, I can say. And at the end, the light will get amplified. And as we already seen, the atoms from high energy level are always making a downward transition to lower energy level. Now, when this happens, suppose if the population of atoms or the number of atoms at lower energy level becomes greater than that at high energy level, the population inversion will stop. So population inversion is basically when you have more number of atoms at high energy level than the low energy level. And when stimulated emission takes place and it continues for a long time, resulting in light amplification, and suppose it reaches to a stage that the population of atoms at low energy level gets greater than the high energy level, then the entire process of population inversion will stop. So if you want to continue, then you have to give external energy. You have to give further external energy. And the methodology to give this external energy to continue the process of population inversion, you call as pumping mechanism. Pumping mechanism. We will see that very shortly. Now next, let's understand what is an active medium. So to get the population inversion for the stimulated emission, only a very few atoms are going to take part in the process. So you call those atoms as active centers. And the medium hosting the active centers, you can call it as active medium. So this medium can be a gaseous medium or a solid medium or a semiconductor, anything like that. So that medium we call as active medium. So the medium hosting the atoms or the active centers which are going to help to achieve population inversion is known as active medium. So now let's see what is pumping. Let's define what is pumping. So we just told that we need pumping mechanism to give external energy to achieve population inversion and get stimulated emission. So pumping is basically the process of supplying external energy to the laser medium so as to transfer it into the state of population inversion, so as to achieve population inversion. It can be done in three ways. First is optical pumping, that is where you make use of a light source. Next is electrical discharge, where you apply an electric field and cause ionization of the medium, and that can result into an excited state. And the third one is a direct conversion of electrical energy into light. Now we talked about having a metastable state so as to get the population inversion and stimulated emission going on. So let's understand what is a metastable state. So as we said earlier, in an excited state, the lifetime of the atom is very less. It's of the order of nanoseconds. So what can happen is they end up doing spontaneous emission and the atoms can return back to lower energy level. So in that case, you cannot get stimulated emission and population inversion becomes a difficult task. So we need an energy level in which the excited atoms can stay for a longer duration. So we need an higher energy level where the number of atoms can be more than the low energy level, and at the same time they can stay for a longer duration. So such an energy state or energy level in which the atoms will have long lifetime and also prohibits spontaneous emission but helps in stimulated emission, we call as metastable state. And the lifetime at metastable state is of the order of micro to millisecond, which is much better than that in the regular excited state. So, in general, a metastable state will allow for accumulation of a large number of excited atoms at that level of metastable state and thus help in population inversion. Now, next, let's see the different pumping mechanisms. So, there are two different schemes which we are going to discuss here. There are multiple schemes. We will discuss about a 3-level pumping scheme at first. So pumping, as we said, we give an external source of energy and make sure that the number of atoms at a high energy level is more than that what is at the lower energy level, and also ensure that stimulated emission takes place. So let's consider this first figure here. So I have a ground state and I denote it as E1. Then the excited state is E3. Then there is a metastable state in between, which is E2. So what is going to happen is you do this pumping process and you give a form of radiation to the active medium. So the active centers, the atoms which are going to help for the process, they absorb this photon and get excited to the high energy level. But once they reach this high energy level E3, since we said that the lifetime is very less there, what they are going to do is they very rapidly come down to this metastable state E2. And once they are in E2, they are being prohibited in doing spontaneous emission from E2 to E1. So metastable state, the atoms can stay for a long time. So many number of atoms can get accumulated here. So resultant will be that the number of atoms at the metastable state E2 will become more than what is that at the lower energy level. Metastable state that will have more number of atoms than what is at the ground state. So you will get the population inversion. So once population inversion is there, any random photon, any chance photon can come and interact with the atoms, cause stimulated emission, result into emission of a spontaneous photon and a stimulated photon. We can also define the lower energy level ground state as lower lacing level and the metastable state as upper lacing level. Next, let's understand a 4-level pumping scheme. So earlier we had only one metastable state, but now we are going to have 2 metastable states. So you have a ground state of E1, the excited state E4, and then 2 metastable states E2 and E3. So light is being incident on the medium. The active centers absorb the light, get excited to the highest energy level, that is E4, and then they drop down to this level E3, a metastable state, and between E3 and E2 is where the stimulated emission is going to take place. So a chance photon or a random photon acts onto the atoms at the level E3 and it results into new photons by means of stimulated emission. And you get some atoms here at the level E2. So now E3 becomes the upper lacing level and E2 becomes the lower lacing level. And if any non-radiative transition can occur, then the atoms at the level E2 can come down to E1. And once again the whole process can repeat by giving more pumping, giving more external source of energy. Now let's understand the last component required, that is the optical resonant cavity, or another term is optical resonator. So it's very simple to understand if you see this figure. So you have an active medium here. This is where the entire process is going to take place. Then there are two mirrors. One of them is a fully reflecting mirror and the one is a semi-transparent mirror. So the entire process of population inversion and stimulated emission take place here, and whatever photons are being created here, they undergo multiple reflections between these two mirrors. They undergo multiple reflection and at the end they come out of the semi-transparent mirror and you can take out the light. But at the same time you can see that there will be some loss of light also happening. So that loss also comes out of the mirrors and you can take them out. But whichever were lost, it's like a kind of leakage of light. They will not undergo amplification, but the rest, the majority, would have undergone amplification. So suppose if the laser generates a continuous beam, then the amount of light produced by stimulated emission on each trip between the mirrors, to and fro reflection is going to happen, then the total amount of light will be equivalent to the light coming out of the beam, coming out of the entire system, along with the loss of light which would have happened. So the resultant is actually a sum of the amplified along with whatever was lost without amplification, that small fraction which was lost without amplification. So this is how an optical resonant cavity works. So you will understand much in depth about all these things when we look into the different types of lasers, which will be the next lecture. But before that, I would like to just list out the characteristics of a laser beam and end this lecture. So there are four important characteristics. First is coherence, then you have directionality, then monochromaticity, and then high intensity. So coherence is what we already discussed. Coherence means if the waves are coherent, then they don't have any phase difference. They all are of the same phase. So throughout, for a long time, they will be having same phase. Next is directionality. Directionality means the photons will travel in same direction, or the laser will emit only in a particular direction. So if you are seeing a laser beam, then you can see that the width will be very narrow. It's not a wider beam. So because of it being narrow, the beam can actually, the resultant laser beam can travel to longer distances without spreading. So this is the reason that laser beams are used at some exhibitions, shows and malls during any event. Next you have monochromaticity. Monochromaticity, as we said, all the photons will have the same frequency or wavelengths. And last is high intensity. So obviously the laser light has been amplified. It is a very much amplified light, and at the same time it is going to spread in a small region and within a small wavelength range. So the resultant is that the intensity of the laser light will be higher in comparison to what an ordinary light can produce. So that's all about this particular lecture about lasers and the principle behind the working of the lasers. So in the next lecture, as I said, we go into the different types of lasers and see into some applications. Thank you.